if you have an n by n matrix and you want to find the determinant of the matrix, you have to use Gauss reduction to reduce the matrix into an upper or lower triangular matrix. Okay, so first of all, what is an upper triangular matrix, what is the lower triangular matrix, and what is a diagonal matrix? All right, let's suppose that we have an n by n matrix. Okay, A is an n by n matrix, and we first want to define what is the diagonal matrix. So a diagonal matrix, so if we say that A is a diagonal matrix, it means that this is this element. This is what we call a diagonal. We only have the diagonal here. So this is the diagonal part. Okay, so it means this diagonal is what we have. So all non-diagonal elements are 0. So to write this, we can just say that A, I, J are all 0 for any I different from J. Okay, so it doesn't matter if the diagonal elements are 0 or not. Okay, our focus here is the off diagonal entries. So once they are when they are 0, in that case we say that the matrix is diagonal. Okay, now let's look at the upper triangular matrix. So for the upper triangular matrix, we have A, I, J is equal 0 for all elements. So if we say upper triangular, it means that all elements under the diagonals are 0. In this case, we say J is less than I. So all entries are 0 for J less than I. So for the lower triangular matrix, A, I, J are also 0, but in this case, it's for I less than J. So what we are saying here is, for the upper triangular matrix, all elements we have here are 0. And for the lower triangular matrix, all elements we have here are 0. Okay, so this A22 up to A1n and A2n are all 0. So we only have the lower part. So it doesn't matter whether it is 0 or not, but we have to make sure that these elements are 0. And having defined this diagonal matrix, upper triangular matrix, lower triangular matrix, if you want to find the determinant of such matrix, it is very simple, because the determinant is just a product of the diagonal entries. Okay, so if you want to find determinant of a diagonal matrix, you just take the product of the diagonal entries. If you want to find the determinant of the upper triangular matrix and the lower triangular matrix, is also the products of the diagonal entries of your matrix. So what I mean here is the determinant of a matrix A is not this matrix, of course. In this case, diagonal matrix A, the determinant of A here is just A11 times A22 up to ANN. So this is a determinant with the condition that A here is either a diagonal matrix or an upper triangular matrix or a lower triangular matrix. All right, the objective of using Gauss reduction is to transform the matrix into either an upper triangular or lower triangular matrix, such that the determinant can just be the products of the diagonal elements. Okay, so having said this, let's look at some properties of the determinant before we really move to Gauss reduction. So if I scale a row of a matrix with a constant, then the determinant of that matrix will also scale with a constant. If I scale a row of a matrix with a constant, then the determinant of that matrix will also be scaled with the same constant. What does that mean? So if I have two matrices, A and B, okay, such that B is obtained from A by scaling one row, then we will say here that if we scale by K, okay, if this matrix B is obtained from the matrix A by scaling one row with K, then we say that the determinant of this matrix B is equal K times the determinant of A. To apply this, let's consider the following matrix: 2, 4, 6, 2, 6, 5, 1, 2, 7. So I want to find the determinant of this matrix, and it is easy to see that the determinant of this matrix is 2 times the determinant of, because we have 2, 4, 6, so we can see that the common factors here can be 2, right? So this become 1, 2, and 3. This is 2, 6, 5, and this is 1, 2, 7. So if I use this definition, as I say, this matrix represents the matrix B, this one represents the matrix A, and this is K. Okay, in this case, we say that the determinant of the matrix B is equal K times the determinant of the matrix A. All right, then what is the determinant of the matrix A here? The determinant of A is, if I want to use Gauss reduction, okay, I want the entry 2 to be 0. So I can say for 2 to be 0, this is 1, 2, 3. For the second row become second row minus 2 first row. So I multiply first row by 2. I subtract it from the second row. This is 0. Okay? So this is 4. This is 2. Because if you say 6 minus 4 is 2. 5 minus 6 is minus 1. All right. For this one, I want to get rid of this. I say, okay, R3 become R3 minus R1, because we have the same entry here. I don't need to multiply by any constant. So if I say R3 minus R1, this minus this is 0, this minus this is another 0, and 7 minus 3 is 4. So this is the matrix. Now we want to find the determinant of this matrix. It's just the product of the diagonal element. So this is 1 times 2 times 4 is equal 8. Okay? Then with this we can find the determinant of B. The determinant of B is 2 times determinant of 8 of BA. This is 8, so this is 16. Okay, this is the determinant of the matrix B. All right. Another property, if I exchange 2 rows of the matrix, then the determinant will be multiplied by minus 1. Okay, so if I still have a matrix A and B, such that the matrix B is obtained from the matrix A by exchanging 2 rows, then the determinant of B is minus the determinant of A. So this is the first point. The second point, if we add one row to another row, it does not change the determinant. Okay, if the matrix A and B, if the matrix B is obtained from the matrix A by adding 2 rows, one row to another in the matrix A, then the determinant does not change. So the determinant in this case of A is equal to determinant of B. Okay, and lastly, if you have a matrix where 2 rows are identical, then the determinant of such matrix is equal to 0. Determinant of the matrix is equal to 0. If one row is a scalar multiplication of another row, then the determinant in this case is equal to 0. Then the determinant is also 0. Okay, so these are the 4 points I wanted you to know, but we will come back. You will see this in details in a few questions in the tutorial. So let's take an example of a matrix where we apply Gauss reduction. All right, we want to find this determinant. Okay, let's start with this first term. We want to get rid of this. We want this to be 0. So the first row, I first write the first row 1 minus 1 minus 2 minus 3. For this one, if we consider R2 become R2 plus 5R1, then we always choose the coefficient here in such a way that if we sum up these 2 terms, or if we find the difference between these 2 terms, we obtain 0. Okay, so in this case, if you multiply here by 5 times 5 plus minus 5 is 0, minus 5 plus 1 is minus 4, minus 10 plus 2 is minus 8, and minus 15 plus 4 is minus 11. For this one, we also take R3 is equal R3 minus R1. Okay, so R3 minus R1 is 0. This minus this is also 0. 6 minus minus 2 is 8. 1 minus minus 3 is 4. Okay, so at this stage I can even simplify. So it can simplify as we saw here when it is multiplied by the same constant. So it is 2 and 2 multiplied by 2. That's why we were able to find k here is 2. So in this case k will be 4, right? So if I continue, but I'll come back for R4 become R4 minus R1. So R4 minus R1 is 0. This one minus R1 is 2 minus 1 is minus 1. 3 minus minus 2 is 5. And the last one is 4 minus 3 is 7. We are lucky here because we already have 1 0. Okay, so I can write this. I just have to get rid of this term and this one, and that will be all because we were lucky. We got 0 here. So here it's 4. Okay, I can put minus 4 because we also have a negative sign here. Okay, we have negative sign. If we have negative sign here, we have 4 here. So I'm taking minus 1 from here and 4 from here. So let's say minus 4. We remain with 1, minus 1, minus 2, minus 3. This is 0, 4, 8, 11. The third row is 0, 0, 2, 1. And the last one, we already have 0 here. So I want, for the last one, I want to get rid of this one. How can I proceed? I can use this row, okay? So the new R, this is the R2, R4, 4R4 minus R2. Okay? Now we have negative sign here. Let's say 4R4 plus R2. If I multiply this guy by 4, this becomes minus 4. Minus 4 is give us 0. Okay? If you multiply this one by 4, this is 20. Minus 8, this will be 28. And if I multiply this by 4, this is 28 minus 11. 28 plus 11 is 39. Okay? Now, we are happy because we are on a good track. We just have to get rid of this last term. So we don't have enough space here. I have to write it here, okay? So don't be confused. It's just the next step after this part is here. So we have minus 4. First row, second row, third row does not suffer from anything. You just have to repeat it here. And the fourth row is 0, 0. We want to get rid of this 28. Well, I can use this second row. If I say R4 become R4 minus 14 R3. If you do the multiplication, so this is 28 minus 14 times 2. This will give 0. So the second one is 39 minus 14 is 25. Okay? So the determinant is minus 4. This negative 4 multiply the entries of the diagonals here. Okay? So this is times 1, times 4, times 2, times 25. I think this is minus 200. Okay? So you see, it's in general, as I explained before, the idea of Gauss reduction here is to transform the matrix into lower or upper triangular matrix, and knowing that the determinant of the lower, upper, or diagonal matrix is just a product of diagonal entries, then it makes our life easy, okay? So if you were to expand this matrix following any row or column, it would have been very cumbersome. That's why we have to use this Gauss reduction so that it can, you see, in very few steps, 1, 2, 3 steps, we already done. So that's the idea behind. Thank you. In the next video, I'll take some questions where you see different kind of matrices, and you should be able to apply also the properties that I've mentioned here, and for you to have a wide knowledge on this concept of determinant using Gauss reduction. All right, this is all. I look forward to seeing you in the next video.